Hello, everybody, and welcome to episode 81 of the Hyperthesis podcast. I'm Liam.
I'm Pheely.
I'm Patrick.
And I'm Jonathon.
As you can hear, today we're joined by a very special guest, Dr. Jonathon Riddell. Welcome, Jonathon.
Thank you. Thanks for having me, guys.
John, you're currently a quantum many-body physicist at the University of Birmingham in the United Kingdom.
Yes.
Correct?
Yep. That's
and
right.
you completed your PhD at McMaster University, where you also studied many-body systems, and in particular, I don't know if this was your main focus or a side focus, but you definitely studied the foundations of statistical mechanics a little bit.
Yeah. So my thesis topic was statistical mechanics from unitary dynamics. So it's a very foundational approach to getting to statistical mechanics. And I'll just throw in that the PhD was at McMaster, and I was an affiliate PhD student at the Perimeter Institute as well. So I spent a fair bit of time there.
Yeah, that's a common theme with a lot of the McMaster scientists. I always kind of forget that.
It's a good opportunity. Yeah.
Oh yeah, it's definitely worth mentioning as well. And additionally, you actually have a YouTube channel where you discuss various physics topics like statistical mechanics and some other fun things. I saw that you had a kind of physics meme review episode, and I noticed that your channel has over 200,000 views, which is very impressive.
Yeah, it's been a grind to get it up that much. It's a little niche. I do aim at a little bit more of an advanced audience, so I assume at least a third year in math / physics for the topics when I do cover scientific topics. But there's a fair amount of there's the meme review, physical review meme, like the journal, and then there's and then there's also the life in academia, grad student experiences, things like this. Because I feel like being transparent allows other people to understand that their experience is normal.
Yeah, and a lot of this stuff doesn't get really talked about. You kind of just learn it on the job. Like, I didn't really know how grad school worked until I went through it, and even undergrads I talk to now, they don't really have any idea what they're getting into. So it's good to kind of communicate this stuff, I think.
Yeah, and I think there's a lot of people that project a lot of confidence, and they don't like to show the fact that they're struggling. And I think all of us are struggling. Graduate school is a difficult experience. Being a postdoc is a difficult experience. Undergrad's a difficult experience, but a lot of people shy away from talking about it, I would say.
Yeah, so it's really good that you actually get into that on your channel. But before we talk about your work more and your YouTube channel and how you got into physics and science, we have an intro topic to discuss.
All right, that would be me. I do stat mech stuff, but probably not very foundational stuff. I approach it very differently than you, I suppose. I think I approach it through information theory. I don't know if you heard of.
No. Yeah, of course. I would say that a modern understanding of the foundations of stat mech sort of is founded through information theory. I would say that that's a central part of the story these days. Even though, I would say 20 years ago, 30 years ago, the community would be a little bit more split on whether or not that's a good way to approach the foundations.
Oh, I see. All right, so the intro topic for today is actually about glass. I didn't know that much about glass. I don't think I know that much about glass, but I found this news article and a paper that came out in January this year on basically how they understanding the process of creating glass. Because during the creation of glass, usually, just to give a little background, glass are very common, very ubiquitous, but what we see are actually not a stable states. When you say stable, I say stable, I usually mean like the lowest free energy state, and they are usually last a very, very long time. However, a glass can also last a long time, but we call these systems metastable, in a metastable state, where it's actually somewhere in between unstable and stable. That's a fast and loose way to put it, I guess. But it's not the lowest energy state or the state that it really wants to be in, it can stay in that state for a long time. Oh, I think we talked about this before in the podcast about, well, maybe everything is metastable.
Is this related to I've heard of this before, but I don't have any citations to back it up, but, when you think of glass, you think of, like, it's some kind of crystal, and it's not like a nice ordered crystal, it's there's some name for it, I can't remember.
Amorphous, I believe.
An amorphous crystal, yeah, so it's like, I have a window in
It's
front of
not
me,
a
it's made
crystal.
of no, well, people call it an amorphous crystal, but it's not really.
Well, we call it
Or
it's amorphous, but it's not crystal.
okay. But, it's a solid material, um, however, there's these really old, kinda like stained glass windows in churches that are very old, and it turns out that, like, over hundreds of years, the glass actually starts, like it flows over a time scale of many, many years. So even though it's solid, if you wait long enough, it behaves kinda like a liquid, it'll slowly flow, so I've heard of, like, these glassy transitions and things like that. I don't know if what you're gonna talk about is related to that at all.
Well, well, okay. Let me put a little bit of background, and then usually crystal or crystalline structures mean there are repeatable structures inside. Usually, you have, let's say, the primitive cell, or the smallest building block. You just think of like the table salt, right? Sodium chloride. The crystal structure is cubic, simple cubic. So think of a cube, and the microscopic structure of salt, of table salt, is also a cube. If you look at the molecules make it up, it forms a little cube inside that makes this microscopic cube. But what's special about amorphous solids are they are not exactly repeatable patterns. They are just it looks like some random uh, configuration around, but they form a solid. So one may think, well, it could not, then the structure might not be very strong. Well, that could be true too, right? Like glass are quite brittle, but there are also amorphous solids, like certain type of glass, tempered glass is quite strong. So there are ways to make it strong too. And what you're saying was correct that you know over time these things degrade or like disintegrate basically because it the well usually like glass for example is like silicon, right, made of the silicon oxides of silicon, and in this like atmospheric pressure and temperature it really doesn't want to be in the form of glass. It's kind of want to be something else. Maybe was it quartz or something. So it kind of, but we force it to be glass and to stay there. But it's gonna basically disintegrates over time. That's in the same with diamond actually, because diamond form underground in high pressure, right? So when you take it out of high pressure, it's a metastable state. So eventually it's gonna go away. So diamonds are not forever. Um, but that's not the point of the story. Oh, not the story. The intro topic for today. So I just learned that to understand the formation of glass, there's actually this nonlinear, irreversible process that happened during the formation of glass. So when you heat your material up and then cool it down to the glass temperature, so there it would basically go through this kind of glass transition. But this glass transition is kind of an out of equilibrium system, and people really have struggled to quantify that. And so it goes from at the glass transition temperature, and then go to this non-equilibrium process, and then relax into this metastable phase where it becomes glass. And this year, they basically found a way to measure this, what they call it, I think, relaxation constant or something like that. And basically using light to probe it. So the way they people understand this process is quite challenging. So they have like I think use visible light and X-ray to find some kind of correlation between parameters that you get to really try to understand this they call it the aging. So glass go through this aging process. where before it's kind of non-linear system where it's and also irreversible. So they devised a method to basically define a parameter that make this process understandable in the standard equilibrium and linear system and reversible system. So I think this is called the relaxation time of each glass. Each different glasses should have different relaxation time. And before it was like a theory on how people are really gonna are understanding it, but we had no experimental method to really probe that. So in 2024 January, Till Bomber, which is from the University of Darmstadt in Germany, basically devised a way to create a system to probe this kind of relaxation time or material time for glass. So I think I would like to basically bring that up to maybe give some information about glass, because glass is one of the amorphous solids, actually one of the hardest thing I think that we don't understand right now. I think we know a bunch of mechanism to it, but this process of for example, why are they not really crystallizing? There are lower free energy states or phase that are available. Uh, Um, but we know how to get to the glassy phase. Usually, maybe you do it slow, you do it fast, right? There are different method.
It's sort of like a pre-thermalization phenomenon, almost. If you guys have heard of that, is that something you guys are familiar with?
I've
I'm not.
heard of it. Yeah.
So I guess like there's one way to look at these problems, and it's like very specific, glassy phase problems, and there's sort of like universality classes of dynamics that you can think about. And what you're describing sounds a lot like pre-thermalization when a physical system is really close to an integrable point, but it's not integrable. It will relax into a metastable state that will eventually like sort of evaporate like over time. And that's basically, I'm not saying that that's what glassy physics is. There's glassy physics phenomenon that people are interested in right now in very, very quantum mechanical problems and like the Heisenberg model. And that's essentially the explanation. Did the authors did you come across like these must be extremely long timescales that we're talking about here? Like what was the experiment like that they were able to extract this?
Um, I know that the fluctuation time scale is in seconds, like for
Oh,
fluctuation.
I see.
So
Yeah. Okay. I guess that makes a lot of sense.
yeah, so they basically can use high frequency wave to probe the system because the fluctuation time scales are so long. Yeah, I don't know about the experimental setup that well. I just, from my cursory reading, it seems to use multiple wavelengths of light to do it.
Interesting. Yeah, I'm not too familiar. I guess.
I think the only glassy physics I think we talked about it once before, and I talked about it in the context of ironing clothes, because you had like polymers in the clothes, and when you heat them up and make them more add more water to the system, you basically like change a glass transition point of temperature, and that's why like you can get a crease. It's like this little solid thing is because you change the glass transition, you form it into a shape, and then you go back over the glass transition, and that's the only stuff I know about this stuff.
Yeah, maybe because the mechanism of phase transitions are quite well understood, at least through like
Yeah.
Landau and those guys is second order phase transition, first order, but the glassy transitions, well, maybe I just don't know. I don't think there are a very well or well written description of how exactly the mechanism work. We know how to achieve them, but I don't know we know the actual transition mechanism.
Yeah, I was about to say the only like whenever I see glass transitions and glass physics being thrown around, it's mostly experimental stuff. It seems that we have a pretty good, I guess, experimental understanding. I mean, I'm sure there's areas where that doesn't apply, or there's certain fields of study in this area that it doesn't apply to, but yeah, I guess like a theoretical model or mechanism is something we don't fully have yet compared to the experimental stuff, maybe.
Yeah, have you guys come across something that's like sort of a minimal model for such a transition? I don't think I've even come across that. Like many body localization is something that does have glassy dynamics, but I don't think anyone would claim that this is sort of like a one-to-one problem.
Yeah, I've never seen a minimal model for it before, but again, I haven't really looked.
I was trying to imagine the simulations to make like how do you prove it's solid too, right? Because it's amorphous. Well, for crystal is kind of easier, and even because I think the distinction between fluid and solids are more clear when it's from crystals. But when it's amorphous, well, maybe you can put some kind of test stress or strain to it to make sure it's solid. And but I don't know. I don't know much about amorphous systems or like simulation into an amorphous system because usually people care more about crystalline systems, and maybe it's easier to do crystalline system. You try to basically minimize the free energy, right? You just and things supposedly go into the crystalline phase if the conditions are right.
Yeah, well, at least in physics, right? You tend to start with the easy things first and then slowly build up to the hard things. So, a nice ordered crystal, I mean, those are hard enough as it is. And now you've got something that's a solid, but not quite a nice ordered crystal. And I imagine that's pretty hard compared, at least like theoretically, to deal with. Maybe I'm missing something, but
Yeah, I mean, what I do, well, for my research, we call it digital alchemy, right? We try to find well, we try to create, well, we call it basically an inverse design instead of coming from like a particle shape, creating crystals. It's forming crystal and ask what particle shape create that crystal. And we can do somewhat, well, quote unquote, alchemy to it. But, that's a story for another day when my project goes, let's get some more results. We'll see.
all right, Feely. Well, unless there's any more comments on that, thank you very much for that intro topic. And now we can move on to the main topic. So today we're gonna talk to Jonathon about his research. So, John, uh, tell us what you do.
Yeah, so I guess I'll start with the topic of my PhD thesis, just to like set a field of like the overarching goals of the of myself and a lot of people in the field. I I like to think about things in a much more sort of like abstract and general way. Like I don't think I have any particular model in mind when I approach the physics. Minimal models for specific types of behavior are which is why I brought that up is very desirable. Yeah.
Yeah, I'm a big fan of minimal models. Like I think Michael Berry, he always trash talks people when they call things toy models because he's like, it's not a toy model, it's a minimal model.
It's
Um,
a nicer way to sort of put that in a sense, because it feels like most of physics is really, there's lots of simple harmonic oscillators, there's the Ising model, and it's like why do we beat these dead horses so much? And there's such beautiful physics that you can extract from them.
yeah, like, why do we approximate a cow as spherical? That seems crazy. Well, it turns out, like, on some scales, it's a really good approximation. It's a minimal model. We don't care about the shape of their legs or horns or whatever.
Yeah,
So you're getting like you're getting the essential physics without all the noise, and sometimes that's bad, but a lot of the time it's not. It's pretty good.
Yeah, exactly. Really being rigorous about all the details in a model, you basically can make the system too complicated and you miss the physics that you actually care about. And so that's the core philosophy, like Liam's saying. You want minimal models. You want to study the simplest possible version of of the type of physics that you care about, because otherwise the problem will end up being too hard. Like the minimal model is also, just because we're calling it minimal, it's also an extremely difficult. It's an extremely difficult problem to simulate or to study. Many body physics problems or any physics problem that people are studying, right? So the overarching, like the as I said previously, the title of my thesis was statistical mechanics from unitary dynamics. In the past, like 20 years, like as I was mentioning to Pheely, there's been like sort of like there's sort of been like a revival in the interest of the foundations of statistical mechanics. So you might it may not have occurred to you that it's sort of like a wonderful thing that temperature is such a reliable number to quantify, macroscopic properties of our experience, right? It's kind of, if you think about like the millions, trillions, however many particles there are, in whatever unit of measurement in the room you want to take. I mean, it's kind of remarkable that it really comes down to a few numbers like pressure, temperature, volume, number of particles maybe is important. It's kind of like a very, very beautiful thing, especially once you go through the sort of trauma of learning undergraduate physics and learning how difficult it is to solve these equations for just a handful of particles. Like a trendy topic is the three body problem, this new Netflix show, right? And we don't have a closed form solution for that, and yet we can make these beautiful statements about many, many particles for some reason.
Yeah, exactly. Like I was gonna mention that show. I mean, I haven't watched it, but even having 3 particles interacting with each other, the mathematics gets crazy complicated because of chaos and things like that. So, some if you've taken high school chemistry, for example, you've heard of PV equals nRT, the ideal gas law. In this room, there's millions and billions of particles flying around, and, you don't have to individually understand what each of them are doing. You can kinda just characterize them all by this, and at least, in the simplest form, this simple ideal gas law with pressure, temperature, number of particles, so volume, like, it is remarkable when you word it like that.
Well, I would actually push it more generally too, that the use or the understanding of statistics is quite relatively new compared to other branch in mathematics, because geometry has been around almost in the beginning, right? And and a lot of things like algebra and arithmetic came way before, and but the like to understand the or to realize the significance of a mean, for example, came much later, or average. Like, by just adding and dividing, you get this number that are useful, but they weren't useful for a very long time. I don't know if you agree with this, but I don't think I see many ancient um, mathematicians use statistics. I feel like that's something that came much later on in the history of mankind.
I think you're like I can't think of any situation. It is like a very, I mean, maybe not modern, but it's a very recent, like compared to other things that you might learn it like in mathematics. It's an extremely sort of recent tool set that can be whether it's like machine learning and AI or it's describing macroscopic properties of particles. It's an extremely robust framework for people to make progress in science.
Well, I mean, we had Bayesian statistics for those machine learning stuff too, and even Gaussian and stuff. Gaussian shows up all the time, like the normal distribution, and people use it for almost everything now, economics to life science to sports to biology is everywhere now, right? To like this is very useful.
Exactly, it shows up everywhere. But coming back to John, so how do you use it in your work?
Okay,
Come back to what you do.
yeah, the interest, especially with the sort of with like the sort of quantum information revolution, people caring about quantum computers and things like this, we've made a lot of advances in our understanding of quantum many body systems through sort of like information theoretic approaches. And so basically, like a really basic question you can ask yourself is if I have an isolated quantum system, it's its own whole universe, and I let the dynamics go and the system run. Why do I expect, with such a complex, exotic system, why do I expect something like statistical mechanics to emerge from those dynamics? Like, there's some technical reasons why that might not be extremely obvious. Like, for example, you could start the system off in a pure state. Now, the that's kind of a technical point, but like a very statistical mechanics is basically getting down all of your properties in the system that you could measure to basically being well described by, say, in our example, a temperature. And the core idea is that a pure state can never actually do that. And the reason for that is that what's called the Gibbs ensemble, the thing that has the temperature that tells you all of the properties of the system, that's a mixed state, and a pure state can never be a mixed state, right? We don't have to go into the details of that. So right from the get-go, it's sort of confusing about why you would see statistical mechanics emerging in a system like that. But actually, what you end up having is that if you picked, say, a qubit or a fermion or something like that, on a lattice in some type of material, a solid, it turns out that when you actually do the measurements, they still look thermal. They still look like statistical mechanics. They're still well described in equilibrium after some process happens. They still look like you would actually expect them. And so this is sort of the exotic sort of context, the most extreme context you can ask, why does statistical mechanics emerge? And that's what I focused on in my PhD.
So I think there are two questions for that actually, because the framework or the setup of the problem sounds like these two questions I had in my mind for a long time. Sometimes I lost sleep over it. First is, why does the system maximize entropy? Because I think that sounds like how you set it up. So if there are this complex system, why is it evolve dynamically in the specific way? And the way I hear that is like, well, why do things maximize entropy? And the second question is, what do you think is really entropy? Is it just the counting of multiplicities or number of microstates, or the more like a Clausius type of definition where it's like, the change of heat over whatever the quantities? Like, what do you think is entropy? And does that a main investigation of your research? Because I thought, I still think that what is very fundamental to statistical mechanics is entropy. Maybe because I approach it to information theory, where entropy is basically almost like the founding principle or the giant pillar where statistical mechanics is derived from.
Yeah, so I would basically be on the same page as you. I think like I'm going to say something a little bit more radical than what you said, and I'm basically going to say that statistical mechanics is just as physical of a framework as any other form of statistics and any other form of field. It's actually not a physical theory. It's a statistical theory of physics, and that makes some people uncomfortable. Entropy is just an information theoretic quantity. It just so happens that the way that particles and things like to configure themselves maximizes entropy. So we actually get very simple distributions when you look at the statistics of particles, and that's really why other frameworks that use statistics work. Is that the fact that the fact that the most common distribution is a Gaussian, right? It's a unimodal distribution with a high peak in the middle. It's well defined by two parameters. Like at the end of the day, things have what we call typicality. Most there's extreme examples where systems don't have this property, and those are very interesting. But for the vast majority of systems, quote unquote generic systems, states in the system are typical in the sense that if you randomly sample them, they look like the Gibbs distribution, they look like the thermal distribution.
Okay, I see. Because when I was when I was starting my PhD, maybe it was my master, I was deriving, following Shannon's and Jane's through their information theory and stat mech stuff, and it's fascinating where how, like, for a very simple thing, like you have a simple system and you basically put it over with one constraint and you maximize entropy, you get a Gaussian distribution. And to me, that's really profound, because you have almost like kind of random system and you look like uniform, and you put some kind of constraint on it and you maximize your uncertainty in your system, which I think was called entropy. Then you get this Gaussian distribution. And well, but that system doesn't have to be a physical system. It can be auto system. It can be just some abstract mathematical system. It could be economics. It just need to have this kind of randomized, or like, statistical, or the number of elements has to exceed certain threshold. Like I think for physics, it'd be the thermodynamic limits, and things start to behave more like statistical thing.
For sufficiently sort of chaotic quantum models, I mean, you don't even really need to go to that many particles, to be honest. But yeah, I really vibe with you bringing up Jane's principle of maximum entropy, because that's really the core argument here. At the end of the day, that's so we don't have to get into philosophy, but there's sort of subjective statistical mechanics, and that's where Jane's comes in. And then there's sort of like a objective or sort of ontological statistical mechanics, where there's some underlying reason, which could also be a valid way to look at it if we could actually prove that, is that there's some underlying reason why statistical mechanics works out so beautifully. But at the end of the day, Jane's the principle of maximum entropy basically tells you that, okay, I don't know what these particles are doing, but I might know some macroscopic information about them, like their temperature, the volume of the system that they're sitting in. And basically, what I can say is I'm going to choose the most unbiased probability distribution to describe their collective behavior. And it turns out that that works very easily if you just know, say, the energy of the system. You get the thermal distribution, and out pops, as sort of like an abstract mathematical quantity, the temperature, right? Like people seem to be very attached to a much more physical interpretation of thermodynamics and statistical mechanics. Actually, all of the hate comments I get on my YouTube channel are related to the fact that to me this all feels like statistics, and to me that doesn't actually ruin the beauty of the problem. It sort of makes it even more interesting, and it actually goes back to your example of sort of glassy physics, because glassy physics are the type of physics that you don't get this behavior, you don't get this typicality. You have states in your system that are very relevant for dynamics that don't thermalize, and they don't have sort of this this equilibrating behavior in the same way that more chaotic and thermal systems do.
Well, I think most of the statistics, well, I think all undergraduate statistical mechanics are all equilibrium statistical mechanics, including most of the graduate courses in statistical mechanics, especially is like if it's the first one, right? We talk about equilibrium systems and how to all these techniques to deal with these types of systems, but they're all equilibrium system, because the non-equilibrium system, I don't think we have that much of a, well, not in the same degree of understanding as equilibrium system.
Yes.
I know now, I think we have like a computer simulations deal with those stuff, but I don't think we have a framework that I think, okay, I think there are framework would deal with it. I think my friend talked about in the journal club before, some kind of like, so major thermalization or something. I need to think about it.
Yeah, I definitely agree. And most undergraduate and graduate level courses actually skip the question that we're talking about. They sort of, for example, the thing you start with is, for example, there's I guess I shouldn't name names, but most textbooks will basically start with something that's called the equal a priori probability sort of postulate, and they'll basically just say, well, I don't know what the states are doing, so I'll just assume all of them um, are sort of they'll have equal probability. Each state has equal probability, and I'll just sort of walk away. And there's really no physical intuition sort of assigned to it. And even though it can be sort of elegantly explained by Jane's principle, like Jane's principle sort of like erases the mystery of this. I mean, a lot of professors will introduce things like the ergodic hypothesis, which isn't actually necessary to achieve thermalization. So it's not sort of like rigorously foundational or necessary. Jane's principle just gets you there with sort of minimal assumptions on what the system is actually doing.
I see. Because like to me, the assumptions are quite reasonable. It makes the intuitive sense. If you don't know anything about the system, we should assume that every state should have the same equal probability. But in a sense, that's an assumption where, well, do we know that's true? Well, we don't know. I mean, we kind of has to assume it, or do we know? I don't know. Like, what do you
Yeah.
think we know?
Yeah, I think it's really interesting because like I think when you're learning physics in undergrad and graduate school, what you do is you go through, you learn things like Newton's laws, you learn like like Lagrangian equations of motion, you learn quantum mechanics, Schrodinger's equation. All these things are like very fundamental, and they describe things in a way that feels sort of like ontologically true, in the sense that we're really getting down to like the framework of the universe, right? And then you jump into a thermodynamics class and a stat mech class, and it's just like they also present it in a similar way, where it's just like, well, this is the way the world works. But at the same time, you're like, well, I just introduced statistics, and you just gave me a very shaky sort of a shaky sort of reason why, okay, we should start with a uniform distribution. But it all feels sort of like the framing seems very strange and counterintuitive, or at least it did for me when I went through undergrad initially, until I was introduced to sort of more modern ways to think about these topics.
Yeah, I, I think that's true too for other things, like, what is a wave function in regular quantum mechanics? Like, we have, a lot of people can answer that, but no one actually truly answers it in a
Or
good
how
way.
does a wave function collapse?
Yeah, that's something else that people study a lot. But yeah, I would like, if I always say this to people, but if I could do an undergrad, if I could like freeze time, redo my undergraduate degree, and then unfreeze time, without having wasted my life at all or whatever, I'd love to do that. Doing an undergraduate degree from scratch with the knowledge I have now would be incredible, because it turns out there's like these really simple things that you learn, and there's actually really deep kind of questions that they glaze over and stuff like that. So it's anyway. Oh,
Well, I mean, when I first learned about statistical mechanics and thermodynamics in undergrad, I didn't like it at all. I didn't think I would be doing PhD in statistical mechanics at all, because I thought like you said, the foundation was kind of shaky when they were taught, right? Like, just accept this, and these come out, and those things that we accept, they weren't like very intuitive or human experience that we see in daily life, or something that, I don't know. For quantum, there's a lot of formal mathematical structures that oh, this new stuff. But for stat mech, like, well, just that's it. That it's not super rigorous initially, right? So yeah, there was quite the change there. When now I actually look it through information theory, I see the profound meaning of it.
so this is like a little taste of what you did during your PhD, John. These very subtle questions that are often overlooked, approaching them and trying to better understand them. So how is this actually carried through to your research now? So you're doing a postdoc, I'm
Yeah, so
assuming.
yeah, so I'm a
Yeah.
postdoctoral fellow. I'm working with someone named Bruno Bertini, and so a little detour is that when you reevaluate these things, is that you find that the topic of thermalization, approaching these thermal distributions, is intimately linked to something called quantum chaos. Quantum chaos isn't like classical chaos. Classical chaos, a lot of people think about like the butterfly effect. Um, and sort of like little changes in initial conditions can radically change the way dynamics look in the future, sort of something like that. Quantum chaos is really basically talking about correlations, or sort of like statistics in the spectrum of physical systems. So this was originally proposed, I think, by Eugene Wigner when he was studying the spectra of nuclei, or something along these lines. I haven't read the story in a while, but basically what you find is that chaotic systems that have a classically chaotic limit, right? So if you take a system and you take it to its classical limit and it's chaotic, those systems will have statistics in their energies, that the potential sort of energies that the system can take. Those look like the spectral statistics of a random Hamiltonian. So just take, build your matrix out, build your model out, and sort of like give it almost like random interactions. The statistics in the spectrum look identical to a random Hamiltonian.
Oh, there's one thing maybe I want to clarify a bit, because when I think of chaos, is inherently in a deterministic system. I thought it was chaos. Mean they're in this deterministic system and there's chaos, but isn't quantum stochastic? So how is chaos? What do you mean by quantum chaos when maybe my understanding of chaos is limited, where I think it just exists only in um, deterministic systems.
Well, I guess the outcomes of measurements are stochastic, but the actual dynamics themselves are deterministic. But there's also a fundamental problem in the dynamics in the sense that they're linear. The unitary dynamics is linear dynamics, and so actually you can't have sort of like a butterfly effect directly when you're just looking at sort of trajectories of individual states in quantum mechanics. So there's been attempts to sort of recover something that looks like a quantum butterfly effect, and we could talk about that. But basically, like from like that's actually something I did a lot of my PhD was looking at the quantum butterfly effect. But actually, that's not actually directly linked to chaos in a rigorous sense. Chaotic systems will have a quantum butterfly effect as well. But basically, the core statement is an unsatisfying statement, and the unsatisfying statement is that quantum chaotic models are models that their classical limit is classically chaotic, and their spectral statistics look like random matrix Hamiltonians spectral statistics.
We had an episode in the past where we talked about chaos, and I think we even maybe talked about quantum chaos because I remember talking about what you just said a little bit, although we didn't get into the random matrix theory, I believe. So if you're listening, maybe go check that out if you're interested.
Yeah, so this was a very hot topic in say the 80s and stuff like that. But when people started reevaluating statistical mechanics, what they found out is that the description that allows you to get two thermal distributions at equilibrium, like that description is called the eigenstate thermalization hypothesis. It's one of my favorite things in the whole world. It's like the coolest. I mean, if I was ever to tattoo an equation, I will never get a tattoo, but if I ever tattoo an equation on myself or, put an equation on my minivan, it'll be the eigenstate thermalization hypothesis. And basically what it is it's like a sort of a generalization of a statement you can make in random matrix theory. And what you find when you study these things is that in classical mechanics, chaos and thermalization seem like basically separate statements, like separate but complementary statements. But like at their core in quantum mechanics, they're basically the same thing. Or thermalization, the eigenstate thermalization hypothesis, the thing that explains thermalization, and the thing that we haven't proved anything about it yet. We've proved some things, but there's no rigorous proof of it yet. It's basically a generalization of random matrix theory statements, which is at the heart of chaos.
So in your work, basically, are you doing like numerical simulation? Are you doing like analytical proof? Like what? When I hear your research, like, well, how do you approach it? Are these all pen and paper,
It's
or
both.
these? Yeah.
It's both. It's definitely both. So there's proofs in my work. There's a lot of like these notions of like typicality. There's like there's sort of like this nice thing of what can I prove without making assumptions in quantum mechanics, and there you can use the arguments from typicality and recover important statements for StatMech or the foundations of StatMech. And also sort of like dynamics. Like you can rigorously answer things like like under what conditions will a quantum system equilibrate, like go to equilibrium, like what are the conditions that you need for that to actually happen. And then for example, like a big accomplishment of mine is that we bounded have you guys heard of the quantum the Poincare recurrence time?
I've heard of it, but I have no context for that.
So basically any finite quantum system that has a discrete spectrum, if it goes to if you wait long enough, it will always return back arbitrarily close to its initial conditions. And so that sort of flies in the face of equilibrium. So it basically says that all quantum systems are sort of like any stability you get is metastable, and that's why you need the thermodynamic limit, right? And so we actually bounded in quantum systems under sort of general situations, how big that number would have to be. And unsurprisingly, it's extremely big. Like the Poincare recurrence time is very very large.
We talked about this on this podcast. Um, because that rings a bell, and then you describe it, and here it goes. I think when I talked about the apple in a box theory to you guys, I think it wasn't on a podcast at some point because
Yeah, yeah, it was.
um, yeah, maybe you heard of it, Jonathan. Because a friend of mine, his little brother, asked me about this video that he saw about the apple in a box thing, where it's like, well, you put an apple in a box and you give it infinite time, and there's a chance you open the box up and the apple comes back again because it's possible for it to go like, you know, well, second law of the thermodynamics is a statistical thing, as they claim, right? But each individual um, atoms can fluctuate into higher entropy state, and given infinite time, a very very long time. I think there's a paper on it. The time was very long. It's possible that it's gonna come back to the near initial state or the initial state.
So this is a rigorous statement. It's actually a really simple proof. You can go up and look at. I actually did I derive it on my YouTube channel. Actually, the Poincare recurrence theorem is like a very trivial thing that you can. Yeah, I think a third year student would be able to appreciate it like in its fullest. So yeah, absolutely. This is a very rigorous statement in some sense. It's a silly thought experiment because it seems so wild. But yeah, if you wait long enough, everything will just maybe this is actually the fifth time we've done this podcast together. We might just be we might be a rebound of of a previously like long time dynamics in our universe, right? But yeah, absolutely.
Pretty wild to think about. But that's the kind of stuff you're doing now.
So sorry. I feel like I'm being very long winded, but basically, so now I'm working with Bruno. We're at Birmingham, and Bruno is sort of a thought leader in we brought up minimal models previously, right? And a nice optimistic conjecture you can have about the universe is that every sort of universality class of sort of things that physicists want to study should have a minimal model for things that you can actually ask questions about that universality class. And so things that are, I also brought up this notion of like integrability. Integrability are systems that you can solve and actually work with analytically. The problem with things that you can work with analytically is that, I mean, one, they've been beaten to death because if you can do things by hand, people will do them by hand, and then people are very curious. But on the other hand, the most generic dynamics that you can sort of want to think about is things that you can't make analytical progress on. Like this is why we want quantum computers, because most systems and most problems you can't actually do them by hand, right? Like I don't think we don't have a closed form expression for the spectrum of helium, right? Is that like that's like the trivial things that we can't solve are sort of really funny. So Bruno invented sort of this not invented, but I don't know how you want to use that language, but he's the thought leader on something called dual unitary circuits, and these are minimal models for quantum chaos. So we're sort of like stepping away from the stat mech, and we're asking like very fundamental questions about the spectral properties of specific types of problems. We're talking more about maybe something like a periodically driven periodically driven system where they have a magnetic field and you pulsate signals through it, or it might be better to just think about it as like a physical system you could realize with a quantum computer. And dual unitary circuits are sort of like a special system that allow you to make a lot of analytical progress, and they're known as minimal models for quantum chaos and ergodicity.
So I see. That's in a way basically the way I understand it was basically is like a extended model to try explain more phenomena. Is it kind of like very fun, like basically what kind of work is?
Yeah, I guess like from a very foundational point of view, like the early work was really using this idea of dual unitarity to make analytical progress to sort of like reproduce sort of like expected behavior of systems. So for example, you mentioned earlier that like why do systems maximize entropy? Well, that's something we expect them to do. Can you actually prove that the system does that, or do we understand why? And the thing is, like, you can actually just sit down and write a very, it's, I mean, it might be a little involved, but basically you can prove that dual unitary circuits generate maximally, like maximum what we call entanglement entropy. So it's the thermodynamic entropy on a subsystem. So you can just prove that these systems have that property. They're a thing that you can make analytical progress in. And then from a next sort of order point of view, the next question you can ask is, okay, so we have this model has very special properties, perhaps too special in some sense. Like, for example, you won't build up entropy faster than a dual unitary model. They're sort of maximally chaotic. Typically, dynamics will have this property where the dynamics don't quite look chaotic at early times, but then if you wait long enough, their dynamics will become universal and they'll look chaotic. Dual unitary models don't have this property; they're just immediately chaotic. That's called the Thouless time, and typically it's non-zero. But for dual unitary for dual unitary models, it's zero. So it's sort of maximally chaotic. And so the question is sort of the question that we're interested in right now, or the thing that we just published on actually, or it's on archive, is sort of what happens when you perturb away from the dual unitary point. It's this point that has such special properties that we can make analytical progress. Can we then show that this behavior is stable under perturbation?
Oh, okay. So you take like a minimal model, and then kind of like perturb it into a more complicated situation or something like that.
Exactly. So dual unitary
Yeah.
matrices should maybe be described as sort of the Ising model or the simple harmonic oscillator of many body dynamics, especially in like the Floquet, sort of circuit model regime.
I mean, that's what we do all the time, right? Like, okay, here's some stable theory or description of thing. Let's perturb it, see what happens. Does it still maintain the form of it, or it will just go crazy and just indescribable?
Yeah, I think like what I said at the beginning of the episode somewhere is like, we start with the simple things as physicists and then we tack on more stuff to them and gradually complicate them to to better describe things.
In
Um,
sorry,
oh,
in a very beautiful way, it's almost algorithmic in a sense. Like
yeah.
every time someone finds a minimal model for some type of thing, you can look back in the literature and basically guess the next 100 problems that are going to be solved based off of the fact that we discovered some new way to describe maybe a minimal model or some new way to solve an existing model.
Yeah, it's very much like that, and it's very I think that's kind of beautiful, honestly. It's. But for the sake of time, I think we should move on to some more questions. So that's what you were working on as your PhD, and that's what you were working on now. So I want to kind of ask. It's going to be like a combined question. I want to ask, how did you get into doing science and in particular physics? So that might include high school and your undergraduate degree. I'm not sure where you did that undergraduate degree, but kind of like, how did you get into it? How was your undergraduate experience?
Yeah, it's sort of a weird story. I wasn't a typically strong student. I skipped a lot of class and played a lot of video games in high school. And my plan had been to join the military. And I went and took the aptitude test to get into the military, and I failed the math portion of the test, sort of ironically. And then I had to go back and take some math classes to be able to retake it. I took them, and I actually applied myself. I ended up loving them. And then there were sort of some physics problems baked into the classes, so I then signed up for physics classes, and then I ended up just forgetting all about that path, and I started a undergraduate degree in applied mathematics and physics at Western University in London, Ontario. And I think, like most people, or like most people at Western, anyways, I started really being interested in astrophysics. I went in thinking that I would do a PhD in astrophysics, and then I got exposed to thermodynamics and quantum mechanics. And then, lucky enough for me, a person named Marcus Mueller was hired by Western in the applied math department. He's a theoretical physicist, very much a quantum information person, but he was also working on quantum many body physics from that perspective. And I ended up getting some summer projects with him, and I sort of never looked back, I guess.
So, and then you end up doing PhD with Duncan, right? Oh, not with Duncan, but at McMaster.
At McMaster. So Duncan's group is very close with the group of Eric Sorensen. So like I do analytics, but like at my core, I'm very heavy in computational physics. Eric Sorensen is one of the best out there at that, and I really wanted to like sort of hone my skills, get exposed to a lot of different numerical methods to sort of approach quantum many body physics problems. So yeah, I worked with Eric. I have published with Duncan though.
Oh, I see. Because I thought, I thought someone in your group, Liam, does like foundation of StatMech too. Like, was it Josh or someone? Anyways, well, you introduced me someone at Mac that does foundation StatMech. So, anyways, the my question is that how do you get into this science communication, like with the YouTube and things? Because I find that the literacy on science, especially physics, is quite low in general. So, well, it's one of the reasons we do these this podcast too, right? So, how do you get into it? And a lot of physicists are quite introverted. They
Yeah.
we keep to ourselves a lot. And what's that journey like for you?
Yeah, so I like during my undergrad, I tried to start a more mathy YouTube channel, like Khan Academy or I don't want to accidentally misremember names here, but basically, I mean, like at that point, there was no market for it, and I wasn't very disciplined, so I made some very poorly made. The audio is terrible on those on those videos, and then so I eventually just like unlisted them. But I always had in the back of my mind that I wanted to sort of go back because I felt like, I mean, YouTube in some sense, I mean, we can talk about the fact that, I mean, like, it's just littered with ads now and it's kind of like a deteriorating place. But like, on some level, YouTube is just like this amazing platform that, experts can go and educate people for free. And sort of, I definitely appreciated like all of the content that I found on YouTube during my undergraduate degree. So I always wanted to like give back and do that. And then during my comprehensive exams, people were forcing me to talk about and read about a bunch of things I did not care about at all. I found I found the whole experience sort of very very annoying. Um, so I thought to myself like once this is done, I just like I feel like it like this is the time I want to talk about the things that I want to talk about. Like I did a StatMech book in my thing, and I was like, this is so terrible. Like if you read this, like I mean, are you actually going to extract any intuition from it? And I had also built up all these opinions about statistical mechanics and ways to sort of explore it and understand it. So that just ended up being like the perfect time, like the built up frustration of comprehensive exams with sort of like a pre-existing desire to make content.
Well, okay. So, and how's exactly maybe because we are doing it similar things? I find that it's quite a bit of work. Even if it's just audio. Well, we have a little YouTube thing which I need to catch up on, but it's a lot of work, right? To make it nice and stuff. Do you have a background in graphic design or kind of photography, or anything like this at all, or is it all self taught? Like in terms of the technical background of the, let's say, YouTube and video, did you have any, or how do you learn it?
No, it was all a process. So if you go back to my very first video, which is it's such a bad video, but it's my most viewed video because it's like a very easy thing to Google. It's like what is statistical mechanics? And so when people Google it or they type it into the YouTube bar, it comes up all the time. So having searchable content is good, but if you go watch it, it's like this terrible slideshow that I made in PowerPoint, and then with like this awful theme, and my camera was like very tiny in the little corner, and like I had like the sides of it blurred out because I didn't want to like organize my room at the time, but I didn't want people to see that it was disorganized. So it was really a process of like over time I added more and more skills. Like I do my thumbnails on Canva now. I have special software called Movavi for video editing. I did at one point try like trying and doing like podcasts, or I learned how to use things like Audacity and like things like this to like organize audio. It's literally just a learning curve. It's not the hardest, but I find that like actually doing sometimes I have like graphics and things actually happening in the video that I animate. And at one point I was really committed to doing that, but then I quit because it's like such a time sink.
Yeah, I feel like it's it's hard in its own ways, just like this podcast is hard in some ways because, the way we do it is we try and publish something every week, so it's like this consistent commitment. But
Mhm.
then I imagine making like a YouTube video, it's like a lot of bulk work at once. You got to do the research, you got to plan how you want to talk, you got to practice, you got to create all this stuff for it. The podcast is a bit more chill because we kind of just, we roughly wing it. We do prepare stuff, of course, but it's not like I have to give a very precise talk with good animations and things.
Yeah,
So
at
Yeah.
one point I was doing a video a week, and it was like it was
mhm.
basically it would take me about 10 hours to do the research and to sort of write the script and all the equations, and then it would take another 10 hours to edit, basically.
Honestly, I'm surprised it only took that long. Like like this podcast, because there's three of us, the work gets divided a bit better. If one person was doing all of it, it would be brutal. Like, doing one YouTube video a week, I can't even imagine. So that's some hardcore commitment on top of like a PhD and a postdoc and whatever, right?
Yeah, you might find that the episodes for this podcast have been sometime releasing a little bit a day or two later. I've been busy with my research and I do all the editing, right? And it's just, well, it's not too bad, but sometimes when you're in the zone, especially in your theory, because it's not limited into in the lab, right? I just come home and still think about the same problem, and I think we all have this same problem too. Sometimes try to go to sleep, and yes, a very good solution came up in your head. It's like let's explore it, and then 3 hours later, you still think about it.
Yes, yes. I often find myself like going to bed at like 9 p.m. and the next night it's like at like 3 a.m. and it's like all around sort of like when I get ideas, and you sort of have to explore things as you get them, as you said. I also find I find that editing is actually editing the content that you make is like the hardest is the hardest one in some sense, because I always struggle fighting sort of like editor's fatigue, where like near the end of the like at the beginning of the video I'll be like super rigorous. I'll be like deleting all like the mouth sounds and like things like that you don't want to hear, and then by the end it's like I mean probably like 30% of the viewers got this far, so
Yeah, I mean, maybe because I have a little bit of background in video editing, audio
oh, I see.
visual, or audio engineering a little bit back when I was doing what's it called it, short films and all these stuff. It's made it a little easier because I use pretty much like Adobe Suite, Audition, After Effects, and Premiere Pro, and to do stuff. And those tools are actually much more powerful and convenient to do. But still, like an hour-long episode is long,
Yeah, it is
right?
it is
And
long, but actually, yeah, okay. I didn't realize you're like much more of a pro than I'm an amateur. Like that's very you guys are approaching it with a much nicer setup than I am.
Yeah, we wouldn't be too far without Pheely doing his editing for this. I mean, I think Patrick could do it too, probably, but I definitely couldn't. I don't know anything about this kind of stuff. I'm just here to talk physics.
I think the entry point can be easy with like easier software, but the tools that Feely is talking about like have real learning curves, and I feel like it's an impressive skill to have, along with being a PhD in physics.
Yeah, for sure, for sure.
yeah, well, I think my last point to make is like maybe it's just me, right? Because you said your background in physics kind of got into physics through basically kind of what would you call it? Like learning about physics. But to me, I got into physics because of these things, because of the doing audio or doing videos, doing photography, make me
Ah,
interested about physics. Right. So it's come from that point. So I already had those skills before because I was really interested in it. But what I realized, I wasn't really interested in it. I was interested in the principles behind light, behind audio, behind sounds, which are physics.
that's a really cool story.
So I think the one question that we always ask our guests that's coming up is the loaded question. So, Jonathan, what are your hopes and dreams? Who do you see yourself being now that you're doing a postdoctorate? Are you seeing yourself being a professor or working in the industry? or more into science communication? Who do you see yourself being in the future?
Yeah, I definitely don't think it's. I mean, maybe I'll continue doing scientific communication, but I think that I like talking about too niche of things to like make that a viable career path. Unfortunately, I'm going to continue pushing along to I'm going to continue pushing along the lines of academia. Like I still enjoy all the problems that I'm solving. I can feel myself sort of maturing as a physicist, asking better questions and things like this, and developing a better sort of research program. Um, but also like I'm not keeping industry off the table. I'm like because I'm a computational physicist, I'm an expert in high performance computing, making things go zoom and doing hard computations. There's always a place, especially in the quantum computing industry for people like me, I guess. So like I don't know. To be honest with you, like I think I don't know. As long as I'm still solving hard problems, I guess.
Right. But do you plan to change the problems though, or you are planning to just go on tackling this fundamental of stat mech thing, or maybe other things that maybe your side project that will become your main project when you're the boss basically, right? When you
Yeah.
can make projects.
Yeah, so like yeah, okay, that's a great question. I am kind yeah, so I think that in sort of a counterintuitive way, I would almost say that the thing that I'm most interested in on all of these topics is the difficulty in simulating them rather than the actual physics. And so I'm leaning more and more towards simulation, building up my own tool sets so that I can share them like with the community. I'm working on a bunch of things like that right now. So yes, absolutely. So I think that when I work with a lot of physicists, they're very interested in solving the physics problem. Physics kind of first, but I tend to really gravitate, and I think I'll continue to gravitate towards being much more of a broader sort of computational physicist as the focus.
I see. Because I do computational a lot. And, each group usually they have made their own tools or their own packages to solve their own problems, right? And sometimes there are tools that, I mean, I used one for like Monte Carlo now that's made in Michigan. And
Yes.
I don't know if it's so widely used, but, when we all heard probably like lamps and stuff for molecular dynamics. And
Yes. Yeah.
so basically you want to be kind of more like a technician kind of type where creating these packages for people to use to solve the problems.
Yeah. I think lamps is a cool example. I think there used to be like an art form in the field of when people were much more focused on developing in compiled languages, Fortran, C++, C. There used to be sort of like an art form for this. I think that the field is kind of degraded in that sense. So a lot of the packages you run along, you come across that are sort of like more modern approaches to problems. A lot of physicists are developing in like Python now, for example. And these things like happen to be very slow. So I want to be able to like give people modern tools that aren't like limping on the fact that they're also being run on modern hardware. Like I want them to be able to take advantage of the fact that physicists have these fancy machines with these amazing CPUs and GPUs, all without actually having to go down and like work on that level. Because I think and I think that there's sort of a sparsity of support like that in our community.
So are you a fan of just-in-time compilers then? Because I find that they really accelerate the workflow a lot.
They do, and I think they're like I think Julia, for example, is a really good first language. I just made a video on this. I think Julia is a very good first language to get into for scientific computing. But at the end of the day, like the upper limit on how good Julia can be is C++. And so I am sort of a I'm a little biased. I do all my coding in C++. I've never used a JIT language because like they're also it's also not like from the perspective of training people and training students, it's also not applicable or useful in industry. Like in high performance computing, you really want to get down to C++, maybe even Fortran in industry. So I am a fan as like a scientific tool, but I think that serious packages should be written in C++.
Fair enough. I know, yeah, I know someone who might disagree with that I T8 for this semester, but I'm writing C++ too. I mean, with a
Nice.
Python wrapper. So that's I find that like wow, once you learn it, it's much better. But I think we're kind of run out of time too. But I think my last thing I'm gonna say that I think I'm gonna oversell us sometime because we don't have that many StatMech people come along. And I have like a million questions that I usually talk to my colleagues about. But it's really interesting to hear from a person who look at StatMech from a different perspective. And yeah, it's just been great.
Yeah, it's been great chatting.
I knew that's what this episode would be. It would just be Pheely and John talking StatMech the whole time, it's exactly what I wanted it to be, honestly. So thank you very much for coming, John. It was great having you and hearing about your work and also your social media communication work with YouTube.
Yeah, it was a great time. Thanks for having me on.
So before we end the episode with a story, we'll get Patrick to tell everybody how they can reach us and possibly you, John.
Right. So there are many ways in which you can reach out to us and be a guest on our show, much like John was today. Thank you very much, John, for joining us. We have an email that you can send us a message on. We are hyperthesispodcast@gmail.com. You can send us a message with questions or comments, concerns, or if you have something to say about StatMech or compiling for high performance code, feel free to send us your comments on that as well. Also, if you are an expert in your area, we would love to have you on the show, so feel free to reach out to us through our email account. We are also on Instagram. You can find us at the Hyperthesis, where we post updates of when our episodes are coming live, along with some associated pictures. So hopefully you saw the one for this episode with John. We also post some occasional memes or whatever else the poster Liam feels like putting on the Instagram that day. So those are ways in which you can reach us. If you'd like to reach John, if you have questions about the work he's doing or statistical mechanics, you can, of course, check him out on YouTube. Check the link in the episode description. But if you just search Jonathon Riddell on YouTube, you should be able to find the channel quite easily. John, are there any other ways that you would like people to reach out to you?
Twitter and Discord. If you go on my YouTube channel, there's always a link to my Discord chat, which has it's a semi-active community where you can ask more technical questions, and things like that.
Yeah, so go check out John. And if people have questions, I take it they can message you on Twitter or through Discord.
Yes.
Leave a comment on your YouTube videos.
Yes. I apologize. Yes, absolutely. That's perfect.
I know I'll be joining the Discord group and also leaving very angry comments on your statistical mechanics videos.
Yeah, you can tell the Julia defenders that they can come into the comment section on my programming languages videos if they want. Also, Wyatt, your previous guest, is an active member of the Discord channel, actually.
Oh, very good. He's not an active member of our Discord channel, even though he's in it, so I'll have to call him out for that.
Yeah, and maybe the Hyperthesis should start a Discord channel to get some active members.
Oh, no, please.
No. Anyway, if you are listening to this episode, congratulations, you found us. Not through Discord, unless you're sharing it through a different channel. But you can find us on pretty much whatever podcasting service you may use, whether that's Apple Podcast, YouTube Music, because Google Podcast is almost no longer in Canada. We are on Audible. We are based out of Spotify. But again, you can find us on pretty much whatever service you are using. We do also have a YouTube channel as well, so you can go check us out there, where we are decently up to date. Again, it takes a lot of time to process each video because the graphics are really, really nice that we do in our videos. So apologies if there's a delay, but you can check us out there. Leave comments as well about your favorite programming language or statistical mechanics or whatever other strong opinions you have. I think that boosts engagement. So check us out wherever you can find us and feel free to share us, comment, like, subscribe, follow, download. Do all that stuff when you can. And also go join Jonathon's Discord and create some discourse there in the field of statistical mechanics and quantum many bodies.
All right. Thank you very much, Patrick. So, what story do you have prepared for us today?
Well, we've talked a lot about quantum systems and statistical mechanics, and though I thought we would take a step back for the story and look at a history of thermodynamics. So, thermodynamics itself is at the very core relationships between heat, work, and temperatures, with relationships to energy and entropy developed as well. Of course, these systems can be small, so we talked about some small scale things, of course, not too small for thermodynamics, to systems that are the size of the universe. So thermodynamics introduces some interesting situation, and in particular, some interesting laws. There are 4 laws of thermodynamics that we say must not be violated, hence the reason why they're laws. And these unviolable laws are known as axioms for the whole basis of thermodynamics. And they consist of the following 4 rules. Law number 1, or the first law of thermodynamics, is that energy can be transferred between physical systems as heat, work, or matter. For law number 2, entropy always increases in the universe, which is something that we discussed today. Law number 3 is that entropy of a closed system at thermodynamic equilibrium approaches a constant value at absolute zero. And finally, we have the 0th law, which was added at the end, but they thought it was important enough that it goes before everything else. And that's the fact that if two systems are in thermodynamic equilibrium with a third state, then those 2 states are also in equilibrium. So there's a lot that can go on with thermodynamics, and we did touch on some different topics there. But how exactly did the field of thermodynamics come to be? Well, these laws actually originated from a lot of experimental work that had been happening since 1650, starting with the work of Otto von Guericke and the invention of the vacuum pump. Now, we've discussed before that these were made out of 2 copper hemispheres, and they only had grease between them, and by pumping air out of it, von Guericke was able to show that the atmosphere applied pressure. Now, we talked about that in a different episode, but the important thing there was that he was able to develop this vacuum pump. Now, Robert Boyle and Robert Hooke both went on to build an air pump a few years later in 1656, and they noticed a correlation between pressure, temperature, and volume. Now, this relationship was later worked out to what we now know as Boyle's law, and it showed that pressure and volume are inversely proportional. Now, later on, there was more work with different ideas of pressure vessels, including primitive steam engines, and Dennis Pepin's steam digester furthered these concepts of pistons and cylinder engines. And these ideas were later better realized by Thomas Savery and Thomas Newcomen. Now, these were very early developments in steam technology, and they were quite crude, but captivated the scientific community to see what was possible with playing with pressure and volume and temperature. Now, in the 18th century, Joseph Black's investigations into heat capacity and latent heat, alongside James Watt's innovations in steam engine efficiency, contribute significantly to the field of thermodynamics. So they were able to produce a lot of theories and also mechanisms that related to, again, just changes in pressure, volume, and heat, or temperature, I should say. Now, a very famous name within the world of thermodynamics is Sadi Carnot, and his seminal work, Reflections on the Motive Power of Fire, published in 1824, marked a pivotal moment that elucidated the fundamental relations between heat, power, energy, and engine efficiency. For this, Carnot is often hailed as the father of thermodynamics, and we know his name especially if you've taken a thermodynamics class, within the Carnot cycle, which describes these types of conversions between heat power, energy, and engine efficiencies. So by the mid-19th century, so in the middle of the 1800s, we saw the actual first emergence of concepts of thermodynamics all bundled together in a textbook. The first textbook was by William Rankine, which was also followed by the simultaneous development of the first and second laws of thermodynamics by Rankine himself, along with Rudolf Clausius and William Thomson, also known as Lord Kelvin. Go listen to our story on him. The groundwork for statistical thermodynamics was laid by people such as James Clerk Maxwell, Ludwig Boltzmann, and Max Planck. Clausius also introduced the concept of entropy in 1865, which further enriched the theoretical framework of thermodynamics. Now, in the late 19th and early 20th centuries, there were significant advances, so moving away from just concepts that were based off of how steam engines were working. We saw works by Josiah Willard Gibbs, who pioneered graphical analysis of thermodynamics processes, as well as Pierre Duhem, who contributed to chemical thermodynamics. Chemists like Lewis and Randall, who you have definitely heard if you've taken a high school chemistry class, if not a university class, applied these mathematical methods that were introduced by Gibbs to analyze chemical processes, and this further allowed the integration of thermodynamics into various scientific disciplines. Now, thermodynamics is still being actively studied in many different sciences, including modern physics and chemistry, but we even use concepts like entropy and microstates in my field, like remote sensing and atmospheric environmental sciences. So there's quite a lot of power behind thermodynamics. And in terms of statistical mechanics, it's considered a branch of thermodynamics. And it emerged with the development of these atomic and molecular theories in the late 19th and early 20th century, and acted as a good supplement for thermodynamics, but at a microscopic level. So thermodynamics truly is everywhere. Its laws have led to many discoveries and propositions, and truly it controls life itself. So there's quite a rich history and experiments and theories for thermodynamics, and much like Jonathon, we're still seeing a lot of research that are coming from branches of thermodynamics today.
Thank you very much for that story, Patrick. Thank you again, Jonathon, for joining us. And thank you, everyone, for listening to this extra special and extra long episode. We will see you. Oh, yeah, this was a great episode.
I apologize. I can be ranty, but it was a good time.
No, I specifically wanted this one to be longer than what we normally do because I knew Pheely and you would have some good StatMech stuff to talk about. All right, everybody. We'll see you in the next episode. See ya.
Take care.
Bye, everyone.